Oh, welcome back, ladies and gentlemen, and we are in a logarithmic state of mind tonight. We've got some monster new things to learn tonight. It's basically like learning a new language, I like to say. And so a lot of the mathematical concepts aren't going to be crazy new to you. If you feel comfortable saying, 2 to the third power is equal to 8, then mathematically there's going to be nothing crazy new. But we're going to learn this to kind of speak in terms of a new language tonight. And it's going to carry through a real big chapter for us. So chapter is going to be very meaningful and powerful. But basically, as we said here, 2 raised to the third power is equal to 8. No sweat. Everybody's hopefully sitting at home thinking, I agree 100% with that, and I'm perfectly comfortable with that. When you say 2 to the third equals 8, you are speaking in what I call exponential language. Okay? So that's our one form today. We're going to work on converting from exponential into this new language we call logarithmic. Usually we're just going to abbreviate it and just call it logs. And it is a two-way street. We can convert from exponential into logarithmic and back from logarithmic into exponential. But basically the equivalent version of this statement, we would say log base 2 of 8 is equal to 3. And I'm sure that it's going to just completely blow you away. And if you're if you weren't uncomfortable with that, I would be surprised. But so basically, we want to talk a lot about how we got from point A to point B here and so forth. But first of all, pronouncing this correctly is a really big deal to me. When we pronounce that, we're going to say log base 2 of emphasis. Let's underline that word in our notebook, of 8 equals 3. And so we just want to, as we communicate tomorrow in our groups, we want to make sure we're all speaking the same language and communicating it and saying it exactly the same way. So it's log base 2 of 8 equals 3. And I'd like to put a little extra emphasis on the way that you write this little 2 right here. That is a subscript. Okay, and basically what a subscript means is that it's it's below the normal line of writing, as opposed to a superscript where that looks like an exponent. This is a subscript. It needs to be very small, very neat, and very accurately placed as we're doing our work tomorrow. Okay, so what exactly is a logarithm? But basically we're going to say a logarithm is an exponent. Okay, that feels very weird to say, but I think as we look at a few examples, you're going to see why. A logarithm is an exponent. For instance, notice when we took 2 to the third power and set it equal to 8, notice how we rewrote that as in logarithmic form when we converted it. We said log base 2 of 8, and do you remember what we set it equal to? Yeah, we set it equal to the 3, and guess who the exponent used to be? The 3. And that's why we usually say that a logarithm is an exponent. A logarithm is equivalent or equal to the exponent. Now what we're going to do here on this slide is we're going to dive in a little more specifically and try to classify what each of these. The 2 right here, that is considered our base. Okay. The 8 right here is what we like to call the answer, what used to be the answer. You'll notice back when we were in exponential form here, we set things equal to the 8. That was our answer. And then the 3 is what used to be our exponent. So we have our base, our answer, and our exponent. Okay. Perhaps the biggest thing, our number one goal today is to start being comfortable not only writing things as logs, but just basically being able to convert from exponential into logarithmic form and vice versa. And one of the things that I find to be the biggest trick is it's very visual. We're going to say start with the 2 right here, and we're going to say 2 raised to the third equals 8. So as we're converting, let's say right now this statement right here is in logarithmic form, and let's say they wanted me to convert it into exponential. I would just simply follow those arrows, and I would say 2 raised to the third equals 8. And for you, some of you are more visual than others. If you're a visual learner like myself, those arrows are really going to help you. They kind of draw yourself a nice little roadmap. Okay, we're going to try to summarize the translation from logarithmic into exponential form here with some very generic letters. It may feel a little overwhelming, and like most things in math, you're not going to feel really comfortable until we jump in and start doing some specific examples. But let's say log base b of x equals y. And we wanted to translate that into exponential form. I like to draw a little double arrow here indicating that it could go both ways. Think about the arrows that we would have drawn on the last slide. We said we'd start with the b right here, and we'd say b raised to the y equals the x. And that's exactly what I'm going to do over here. We're going to say base b raised to the y equals x. I think your handwriting is going to be extremely important on this chapter. You know, what's a subscript? What's an exponent? What's just a regular letter or number? You know, so the b over here used to be a subscript. Now the b is just a regular generic, you know, letter or number. Okay, again, don't think of it as if you're learning a whole lot of new mathematical concepts today. You're more or less learning a new language. What we have here on the left side, this is your logarithmic language, of course, and then what we have over here on the right side, that is your exponential language, and we're just going to be able to convert back and forth as fluently as possible. One other really interesting tidbit here is what is the domain of a typical logarithmic function? In fact, again, ask yourself, what are we taking the log of? We are taking the log of x, and what we're going to say here is that x has to be greater than 0. In other words, x is only allowed to be positive numbers. Okay, keep that in mind as we go further in this chapter. X is not allowed to be a negative number, and x is not allowed to be 0 itself. Okay, we're only allowed to take the log of positive numbers. Okay, real quickly, a little bit more terminology we want to cover before we jump into some hardcore specific examples. But here's a couple special logs that we're going to see that have what I call implied bases. Another word for implied is kind of an invisible base. For instance, if I just said log of x, you'll notice something's missing. There's supposed to be some number down here after the g, but there is none there. So in this case, that's what we call a common log, and the invisible base is a base 10. It's the most popular of all the bases. You'll notice if you look at your calculator, there is a log button, and what that is that log button is in base 10. So if you do get a problem in base 10, your calculator can help you. The bad news is if we're operating with log base 2 or log base 7 or log base 8, the calculator is no good to us. The other real special one that we need to be aware of is something called the natural log, and it says ln of x. Notice, and these parentheses are optional. I could have put parentheses up here. I could have put parentheses right here. That's optional. Notice again, first of all, there's no log, and again, there's no subscript there. There's no base after the end. That's equivalent to log base e of x. And that might have just blown your mind completely right there. E, we're going to talk a lot more about E, but I want to go over a few basic things here today. You know, what is E? First of all, E is a constant. Okay, that means, what is a constant? You're probably wondering. A constant is not a variable. It's something that's not a variable. It's not going to change. It's always the same. For instance, you probably remember pi is equivalent to 3.14 yada 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 yada. It's a never-ending decimal. It's irrational and it goes on forever. E is very similar, except for E's approximately equal to, and I should have used approximations back here, 2.718 yada yada yada, and that decimal goes on forever and ever. The good news is your calculator does have a special button just for E. We'll talk more and more about him in the future, but just so you know now, I want you to know that this E does exist. It's not a variable. It's what we call a constant, and it's something that's so special in higher levels of math that they created a special logarithmic function just for base E. That's how special E is. Okay, time to roll up our sleeves and get a problem under our belt here. The first one, I want to talk about log base 5 of 1 equals 0. And again, we could put parentheses around that 1. Anytime you say the word of, parentheses are a good idea, but they're optional here. Translating from logarithmic into exponential form, again, I'm a big fan of using some arrows. We say we're going to start with the 5, we're going to raise it to the 0 power, and that is then equal to an answer of 1. So we'll say 5 raised to the 0 equals 1. I'll put a little double arrow to say that we've translated. And I think you'll agree with that statement. Anything raised to the 0 power is certainly 1. All right, number 2. Let's say log base 25 of 5 equals 1/2. Okay, and we're going to go ahead and get ready to translate that. We'll say base 25 raised to the 1/2 equals an answer of 5. So all it is, 25 raised to the 1/2 equals 5. If you have any doubts about that, just remember raising something to the 1/2 power, according to our groundhog rule, is the same thing as radical 25, so sometimes we may write it like that. Either way, they're both equivalent. Okay, one more of those for fun. Let's see, we'll slide down, give ourselves a little more room. Number 3, let's say log base 4 of, here's where the parentheses are really helpful when you start working with fractions, of 1/16 equals -2. Go ahead, we'll switch colors here. So we're going to start with a base of 4. We're going to raise it to the power of -2, and that's supposed to equal an answer of 1/16. So therefore, let's say 4 raised to the -2 equals 1/16. If you wanted to verify that, remember your negative exponents mean we're gonna reciprocate the base. Now change the signs of that exponent, and yeah, those are certainly equal. All right, let's see if we can switch gears here and go in the opposite direction. Number 1, let's say, what if they told me that 3 to the 4th was 81? Okay, they've given me this expression. It's already in exponential form, and they want me to now translate this into logarithmic form. So I'm going to say log base 3 of the answer, which was 81, equals the exponent, which is 4. Just real quick tidbits here. Remember, that first number right there, that's your base. Okay, I'll put a little b. The 81 was your answer, and the 4 is what used to be the exponent. So just those couple basic rules are going to help us out quite a bit here. Number 2, what if they told me 6 raised to the -1 was equal to 1/6? Okay, that's been given to me. It's in exponential form, and it's my job to convert that to logarithmic. So I could say, well, my base was a 6, so I'm going to say log base 6 of, let's see, what was the answer? The answer was 1/6 equals the exponent, which was -1. There she goes. So it's important to understand here that this expression, that statement there, and this one over here, they're 100% equivalent to each other. They're 100% equal. They're just in 2 different languages. Okay, number 3 says 8 raised to the 2/3 power equals 4. Okay, that's the given exponential. We're going to translate that into logarithmic. I'm going to say log base 8 of the answer 4 equals the exponent, which was 2/3. And that's all there is to it. It's as simple as that. All right, we're going to test our ability to evaluate a logarithmic expression without using our calculator. So let's pretend they told me that log base 3 of 27. And they just gave me this and they said evaluate it. So the first thing I would do is I would say, well, that has to equal something. So we'll say that it's equal to x, some unknown value. And I think it's easiest if we take that expression or this equation and convert it to exponential form right away. So I'm going to say, let's say 3 raised to the x equals 27. 3 raised to the x equals 27. And then from there, it's just some nice mental math. We're going to say, well, x has got to be a nice 3, because 3 to the 3rd power is, of course, 27. Okay, same type of idea here with number 2. What if they gave me log base 4 of 1/64th? And the directions simply said evaluate. What is this expression equal to numerically is basically what they're asking me. So we'll say, well, it's equal to something, and for now we'll call it x. If we converted that to exponential form, we'd say 4 raised to the x equals an answer of 1/64th. Here's where we might dip back into our previous lesson, maybe, where we try to create like bases on both sides and we solved an exponential equation. But basically, I could say to myself, well, I know x has to be some negative number. That's the only way you're going to end up with a fractional power. And then I could also say that 4 raised to the 3rd power equals 64. So I'm going to say that x equals -3 in that case. Okay, our third one's going to be the feistiest, as usual. Let's say log base 1/3 of 27. And again, they simply just asked me to evaluate this. I'm going to say, okay, it must be equal to something. I'm going to convert that I'm going to say base 1/3 raised to the x power equals 27. That's what it looks like in exponential form. And again, we're going to resort back to a previous lesson where we were solving exponential equations and we tried to create like bases on both sides. I'm going to try to express both sides in terms of base 3. So on the left side, 1/3 is really equivalent to 3 to the negative 1. That's still being raised to the x power. And 27 is really 3 to the 3rd power. We use our power rule, so we're going to multiply those exponents together on the left side. And then we had this one theorem that said if the bases are the same, we're allowed to simply set those exponents equal to each other, and voila, x equals -3. Okay, we've got one more monster property here to go over, and it's called the change of base property, and it's an extremely helpful property, especially if you have a calculator like a TI-83 that's not there. We can't do the upgraded version. If you have a TI-84 and you're not upgraded yet, make sure you holler at me in class tomorrow, and I'll try to link yours up with mine and get it updated. It just takes about 5 or 6 minutes. But anyway, the change of base property says that if you have log base b, well, I don't know why I wrote a 2 there. Let's say that's a b. Log base b of x. You are allowed to rewrite that as the log of x divided by the log of b. Now, a couple of things you really want to notice there. As I rewrote that, it used to be in base b, but what are the new bases? These are invisible bases. We'll go back to the beginning of our notes when we said we might have invisible bases, or what I like to call implied bases. If there's an invisible base right there, it means there's an invisible 10 right there. Okay, the reason I like this statement here so much better is now once you're in base 10, the calculator's now fair game. Okay, so there's a lot of times where they may give us a problem in terms of a very obscure base. Like, what if they said log base 7 of 33? Okay, a very weird one that we can't do in our head. We're going to rewrite that as the log of 33 divided by the log of 7. There's an invisible base 10 on both of those expressions, and now I can plug that into my calculator. So let's make sure we put some big box around this theorem, or this property right here. It's called the change of base theorem, and it's something we want to be very fluent with. Okay, last slide for the night. We're just going to practice using that change of base property. They're going to let us use our calculator, and but we do have to show evidence of using that change of base property. So maybe they gave us an obscure one. Maybe they said log base 3 of 22. And you'll notice that's not a friendly one to evaluate by hand. Our change of base property says we're allowed to rewrite that as log base 10 of 22 divided by log base 10 of 3. The log base 10 again is called a common log. It's a very special one. Now I could simply type this into my calculator, get a nice decimal answer, and round it to the desired number of decimal places, whether it was nearest tenths, hundredths, or thousandths. Again, just for a little more practice, if they wanted log base 6 of maybe 53, we could rewrite that as log base 10 of 53 divided by log base 10 of 6. Again, these are perfectly equivalent and equal. Now, because they're in base 10, we have these invisible base 10s, so we can plug it in our calculator and again round it to the desired number of decimal places. So I hope you enjoyed our logarithmic state of mind here tonight. Good luck tomorrow, and we'll gradually build our confidence up to a very high level where these logs just seem to roll off our tongue.